Good. Right. You can hear me, everybody? Yes. Okay. Well, welcome everybody. Thank you all for coming. This is our great pleasure here to have Austin Chadwick from Columbia Climate School. Recently started as an assistant professor there, and we're super lucky that he even has time to give us a little bit of a show on his research recently. Austin is a geophysicist by training at UCLA, and then he did a string of postdocs through University of Minnesota, UC Santa Barbara, and then Columbia, and now as an assistant professor at Columbia. Austin is works on uh, deltas and river sediment transport and a whole bunch of exciting geomorphology with physical processes and implications for humans. So, Austin, it's a great pleasure to have you here. Please take it away.
Thanks, Pedro, and thank you to the organizers and everyone for coming. Can you hear me okay? And oh, I think I shared the wrong screen. One second.
Yeah, we hear you.
Hear me? And then my slide should be in play mode. Can you see that okay?
Yes.
Cool. All right. So thanks, Pedro, and thanks, organizers and everyone for coming. I'm excited to share some of my recent work today. Um, I work on river systems, so thinking about their origins, their evolution, and how they're responding to our rapidly changing world. So rivers are these bodies of large, fresh flowing water found across the Earth's surface. And as you can tell from this NASA Worldly image of the Nile taken at night and how much it pops, they're really important population hubs. So something like 3 billion people around the world live along rivers. They're also the arteries of Earth's rock cycle and water cycle. So there's this rivers form from this natural self-organization of uh, runoff and also sediment that's exhumed and eroded from the uplands through the lowlands to the sea, where this material is evaporated and subducted. Rivers come in many different shapes and sizes, and they're really dynamic. So we can get everything from these single channel meandering rivers that form these beautiful loops on Earth's floodplains to these multi-channel or sometimes called braided or anastomosing rivers where nat flow naturally splits and divides into these interconnected channels, subchannels. And then to the sea, where rivers deposit their sediment loads and build deltas that are really dynamic and constantly shifting over time. And importantly, river systems today are facing a lot of changes due to climate as well as human activities. So we're thinking about sea level rise, storm surge, as well as things like damming, deforestation, and the construction of man-made levees. So this brings me to sort of my research vision is I tackle fundamental questions about the origin and evolution of river systems, as well as climate-related challenges and river hazard prediction and mitigation. I use a bunch of different tools to tackle these kinds of problems. The first one being geophysical and geologic field work. So I've done a lot of work on rivers, a lot of times quantifying things like how the water flows, how that transports sediment in the river, and how over decades to centuries that causes the channel to evolve over time. So this is that morphodynamic cycle. I also split my efforts between quantifying surface processes and also the connection to subsurface processes like subsidence and soil salinity and things like that. I also use remote sensing to quantify river processes, taking advantage of this large amount of global imagery and thinking about how we can turn this into improving our understanding of how rivers move. So, for example, quantifying riverbank migration from Landsat, as I'm showing here. I also am a big believer in using theory and laboratory experiments to help improve our understanding of river systems. So these are really cool because they basically allow us to go to the lab and basically speed up time and isolate variables. So here you're looking at an example of a river delta experiment that evolved over around, hundreds of hours at the scale of meters that we can use to really compare and better understand systems in the field that can take place over decades to centuries at the scale of the landscape. And so coming back to my sort of my research vision, my work to date is largely can be categorized into three main topics. The first one being how rivers move, so river mobility. The second being these coastal river deltas, and the third being this connection between rivers and subsurface processes. And today I'm just going to briefly touch on one question that I've been thinking about in each of these topics that I'm especially excited to share. So, starting with river mobility, I'm going to be thinking about this question: what is the origin of different river channel patterns? So, braided and meandering rivers and stuff like that. So yeah, let's get started on that. So the origin of different river channel patterns is one of the oldest, really like longstanding questions in river science. So broadly, we can categorize rivers into two main types. The first one on the top, this is what we call a single channel river, where the flow is confined to one channel, or we can sometimes call them a thread for terminology purposes. And then the second one is on the bottom. This is what we call a multi-channel river, where the flow naturally divides itself into interconnected subchannels. And as you can see from playing this time lapse here from Landsat, that these two kinds of rivers can evolve quite a bit differently, and that can have direct consequences for the flood risks and erosion hazards for people along them, as well as for the carbon stored in their floodplains and the alluvial architecture of their sedimentary deposits underneath. So it's pretty important to understand. Um, and so a lot of previous work has looked at this problem, and one of the really important findings has been that these multi-channel rivers tend to be found in regions with higher water discharges, steeper slopes, and coarser sediment. So here's a nice plot from Ferguson showing just that. So if you look at this is y-axis of slope, x-axis is water discharge for many different rivers in their compilation. And then these lines drawn here are all uh, different studies that have tried to sort of draw a line that divides the single and multi-channel regimes. And I think you can appreciate from this that this boundary is kind of fuzzy. So there's different lines in different places. And we also don't really know about what the physical mechanism is when we look at it from this kind of empirical approach. So later work has improved our understanding of this by basically noticing that these conditions for multi-channel rivers tend to favor bedload transport and have can be partially explained by modeling positive feedbacks in bar deposition. So basically, you have some kind of simplified model framework where you quantify the flow, how that's perturbed by sandbars along the river and how that can contribute to the growth of those bars. And then you vary your sort of initial condition here and say, okay, maybe I have multiple channels, maybe I have a single channel, and then you solve for what's the most stable or the least stable configuration, depending on what model you're using. But the thing is that a lot of these models give us mixed results. So sometimes we're getting less than 50% accuracy when when we go to a river in the field, plug in the values for these models and say, do we think this model should be single or multi-channel? So there's something that we're missing. And I think one of the big pieces of this is that this modeling approach doesn't really think about how the banks of these rivers are eroding. It's kind of focused on the deposition, but not the erosion as well. And we know that bank erosion and accretion have this balance, at least along single channel rivers, that helps them maintain an equilibrium width. So a nice example of this is shown here. This is the Trinity River in Texas. You can see it has a nice constant width along its length. And previous field work has shown that as the channel migrates, it maintains this equilibrium width because the bank erosion on one side is compensated by lateral accretion on the opposing bar over sort of multi-year timescales. And we can quantify this using what I call the normalized differential migration. It's pretty simple. It's a non-dimensional number that's just the erosion rate on one bank minus the accretion rate on the opposing bank, and then you normalize that by the center line. So when this normalized differential migration is zero, that means the erosion and accretion are in balance and we have an equilibrium width. When this number is positive, that means we have net erosion and we think the channel should widen. And when this number is negative, that means we have net accretion and we think the channel should narrow. We can plot the differential migration on a graph like this that I'm going to keep up for the next few slides. It's pretty simple. We just have one x-axis here. Zero is in the middle. That's this equilibrium condition. And then when you go to the right, that means net erosion and widening. And then on the left in this orange, that's net accretion and narrowing. And if we plot the Trinity River on a graph like this, we see that it falls right along this equilibrium line. But importantly, there's experimental evidence that multi-channel rivers don't always follow this trend. So you can look at these lab experiments where there's evidence that bank erosion can actually outpace accretion, causing what's called runaway widening. So here's an example from a SAFL experiment here where it was noted how the initially single channel widens over time and then eventually splits into multiple interconnected channels. And so this has led to this hypothesis that there's these multi-channel rivers themselves might originate from this runaway widening of their channels. But there's a problem with tackling this hypothesis and testing it, and it's that existing methods for quantifying how rivers move laterally tend to be really tuned for single channel rivers. So what I mean by that is a lot of traditional methods basically will take this map of the river and then they'll digitize it in terms of a center line and then track that center line over time using algorithms like dynamic time warping. But I think you can appreciate just from this sketch that this works pretty well for single channel rivers, but it doesn't actually track the widening of the river so clearly, and it also tends to fail when we have these multi-channel systems. So all that is to say, with existing methods, it's hard to quantify del V star across different types of rivers and testing our hypothesis. So that's where we came in. To help test this hypothesis, we developed a new method for quantifying bank migration that's equally applicable across all different types of channel patterns. Briefly, how it works is basically we have time-lapse imagery of our river. If we just zoom in for an example area here, we first identify the riverbanks using various types of approaches. Here we're just using PCA analysis. So this is wet, this is dry. We then track the migration of those riverbanks over time using an algorithm adapted from particle image velocimetry. So this is a tool used to track particles in a fluid in fluid dynamics experiments that we here sort of adapted to track the banks of rivers on a landscape. Basically, how it works is you break the image down into many different sub images. So here's this little yellow square, and then you try to correlate the channelized area from one image to the next and find the best fit vector that describes that. And so it's basically giving us this coherent motion associated with bank migration. We can quantify the erosion and accretion by just taking the dot product of these migration vectors with the bank normal direction. And then we can quantify this normalized differential migration metric we were talking about by just plugging that into our equations till we start. And if we do that for an experiment like this here, you're seeing on the left, this is I think every minute or maybe it's every 5 minutes of the experiment and seeing how these yellow vectors are tracking the migration of the banks. And if we take those vector fields and we plug it into our differential migration metric, we get this yellow symbol on the top right for this experiment. And you can see it's in this net widening part of the regime. So we're getting a consistent story with this hypothesis that the multi-channel rivers tend to have net widening. But at the end of the day, this is just two rivers, one in the field and one in an experiment. So it'd be good to test it better. So what we did is we went to the NASA Landsat satellite archive and tested it through PIV analysis for these rivers. So we took this basically 392 rivers from a database that we started with, where we had data for the thread count and the widths for the threads. Um, and then after filtering out the rivers that were too small, too slow, or too fast for this kind of image correlation algorithm with Landsat, we came up with about 100 rivers, 26 single thread, and 66 multi-channel, sorry, single channel, multi-channel. Um, yeah, and so I'm going to briefly walk you through some of our results here, starting with the Mamore River in Bolivia. So this is a single channel river and it shows the signal of balance between bank erosion and accretion that helps it maintain a constant width. So I'm going to play this NASA Landsat time lapse overlaying with the PIV derived vector fields of bank migration. So every image is 1 year and you can see here that the migration vectors are tracking the coherent motion of the banks over time. And if we take the average differential migration calculated from these vector fields and plot it as a mean here on the top right graph, we can see it lines right along this zero line. So we're seeing the single channel river's got a constant width and a balance between erosion and accretion. But in contrast, if we go to multi-channel rivers, like here in the Amazon and Peru, we see an imbalance. And if, we actually see that there's this differential migration is positive. So here's the Amazon here near Tamxiacu in Peru. Um, and here we saw that erosion actually outpaces accretion laterally and causing this runaway widening effect. And I'm going to play this Landsat time lapse here to show you what that looks like. So here I'm going to play it. It's the same thing, one image per year, and the yellow vectors are the migration. And I want to call your attention to these two bends, which I think are really demonstrative for showing what's going on. So basically, as these threads are migrating, they get wider. And that happens until this sort of point where an island emerges in the middle, and then it breaks into two subchannels. So this is what we think is going on along the whole length of the river on average. So basically, as these channels widen, As they migrate, they naturally widen, then split because they get over widened. And so that's why we think it has multiple channels in the first place. We see similar story when we go to different multi-channel rivers. So here's an example on the Irrawaddy River in Myanmar. I'm going to play that same time lapse. I think you can appreciate that there's a little bit more going on here in terms of we get downstream motion and a lot of these threads are sort of colliding and interacting with each other a bit more. But if you take the average differential migration from this river, we actually get a very similar amount of like on average widening, similar to the Amazon. So putting results together from the larger analysis, I'm going to sort of plot points on the world map and then also plot them on the same graph on the right-hand side here. So this is the same x-axis of differential migration, but the y-axis now I've added is just the number of channels of that river. So starting with these single channel rivers, here in blue, you can see they're all clustering along this equilibrium line with an uncertainty. And then as we add the multi-channel rivers, we can see peeling off of the population into this pink regime, which is the net widening and erosional side. So this is basically consistent with this hypothesis that these multi-channel rivers originate from the runaway widening of their subchannels. And this is pretty interesting because I think it implies that these multi-channel rivers are arising from cycles of width instability rather than any kind of width equilibrium. And this is contrary to what a lot of us learn in geomorphology textbooks and in class about this idea that these rivers, that river channels over time migrate across their floodplain through this balance of erosion and accretion and have this sort of equilibrium form that's moving over time. And instead, what it seems like is going on is that for a multi-channel river, if you look at one example subchannel, over time it's going to migrate, and because it erodes laterally more than it accretes, it's going to widen. And that's going to happen until some point where it gets so widened that the sediment accumulates in the middle of the channel and forms a bar or an island. And then that splits it into two channels, and then that cycle can repeat again for one or both of those new channels over and over again. So you basically maintain this morphology, but it's not an equilibrium. It's just sort of cycles limited by this widening and bar formation. And this is really important when we think to many managed rivers today, which we're increasingly recognizing many were originally multi-threaded. So you would not guess from the LA River's modern plan form, but if we look at it in the past, back in the 30s, it was a multi-channel river. And as we look to the future and think about restoring these rivers and sort of freeing them from these cement banks, it's important to think about what is the natural state of the river and how much is it going to naturally widen over time, what that means for the people and infrastructure along them. So that wraps it up for this first section of my talk. So briefly, we developed this technique for mapping river migration that's applicable to all channel patterns and applied it to the satellite archive. We see these single channel rivers originate from a balance between erosion and accretion with equilibrium width, whereas the multi-channel rivers have this imbalance and runaway widening. And then we think this is important for the restoration of managed rivers today that may have originally been multi-threaded. So yeah, that wraps it up for that section. Now I'm going to shift gears briefly, and we're going to start thinking about coastal river deltas. Specifically, this question, which is how do river deltas respond to sea level rise? For motivation, I'm showing you this image of the Mississippi River Delta, where approximately 30% of the coastal wetlands have been lost since 1900. And even more is expected to be lost in the coming years. And a big part of this is because deltas are really flat landscapes. So you raise sea level a little bit, or you have a storm surge, and it can inundate huge swaths of land. Um, but importantly, river deltas naturally mitigate this kind of land loss by building new land through sediment deposition. And a really good example of this is over on the west side of the delta. This is the Wax Lake outlet, where approximately 50 square kilometers of new land has been built just in the last 30 years or so. And I've been part of teams that have conducted manual surveys, unmanned surface vessel, and shallow water bathymetric surveys by boat to really quantify the rates and scales of land building in these areas. Um, and then, yeah, I don't have time to talk about those in detail, but I want to also talk about other kinds of deltas like the Yellow River Delta in China, which is an interesting sort of compare contrast case because this river is about 10 times smaller than the Mississippi, but carries about 10 times more sediment. I mean, as a result, it's actually gained more land area since 1976. So we have this different balance in the sediment loads. I mean, we've worked here as well using techniques like RTK GPS, hydroacoustic current profiling, and sediment transport surveys to quantify the rates and scales of land building here. But for this section, what I want to do is kind of step back and talk about what we can learn from these studies and other studies about delta response as a whole. And a big part of this is that rivers deposit sediment in discrete lobes on these deltas, and is periodically reroute these lobes through what's called a river avulsion. And I'll show you what I mean by that, starting with our friend the Mississippi Delta here on the left. So we're familiar with the modern course of the river here from the north, flowing to the southeast, ending in that bird's foot. But if we look at the system of a little more than 7,000 years ago, it was actually flowing more due south and depositing sediment in this white shaded area here, which we call the delta lobe. And at about 5,500 years ago, the river catastrophically changed course. It jumped its banks and formed a new path to the sea. And this process is called a river avulsion. It's basically finding a new path of the river. And this started to build a new lobe in this darker shaded gray area. Another avulsion occurred at about 4,000 years ago, and then again at 2,600, and then again at around 1,000 years ago, giving us this sort of modern configuration of the Mississippi Delta. There's a few things we can notice about these river avulsions. The first one is that they tend to have this characteristic length scale. So the location shown by the star tends to be at a relatively constant distance from the ocean. So we call this the avulsion length, or L sub A. And then they also tend to have a characteristic frequency. So avulsions here tend to occur on a sort of a clock, in this case once per 2,000 years. And we see similar patterns when we look to other deltas like the yellow, but they can manifest at different scales. So in this case, the avulsion frequency is more like once per decade, and the avulsion location is much shorter, so about 75 kilometers. I just want to mention that river origins we think are the origin of the river delta's size. So that you can see this length scale here is kind of telling us the scale of the river delta plain. And this is basically because this triangular shape that we associate with deltas is really defined by this hinge point where the avulsions occur over decades to centuries. It's basically where the rivers hit the hinge zone where it's bopping back and forth. And because river deltas are named after this the shape of the landform, this after this Greek letter delta, you can also think about it as being the avulsions at the origin of their name. So all that is to say is that I think to understand how deltas respond to sea level rise, we need to understand how the location and frequency of these avulsions responds to sea level rise. So what does past work tell us? Well, avulsions we think occur in part because there's this deposition that occurs in what's called the backwater zone. So as if we take a long profile of the Mississippi River here from A to A prime, here's the elevation of the riverbed and the water surface in blue. We can overlay the location of the avulsion and its length here, LA, on this profile, and also notice that it corresponds pretty closely with what we call the hydrodynamic backwater length, or L sub B. This is just the ratio of the flow depth to the slope and basically describes the zone of gradually varied flow where the flow from the river is also affected by the standing water at the downstream end. And if we plot the avulsion length versus the backwater length scale for the Mississippi, for the yellow, and for several other deltas in nature, as well as scaled laboratory experiments, we see this kind of scaling relationship. So we're starting to get at where the avulsions occur on these deltas. Another important thing is that we think these avulsions occur when channels basically elevate themselves to a threshold height above their floodplain. So if we look at this cross section here from B to B prime on the yellow river delta near the avulsion site, here I'm showing you this elevation versus distance across the channel. This is at some reference time. And then if we look at it right before an avulsion occurred, you can see that it builds up sediment in the channel, and it builds up sediment to a height that's comparable to its own depth, often like we see in the field, like maybe half a depth or even more. And if we plot, we can basically take this time scale, which is the rate that we think the channel fills up to a height comparable to its depth. So it's this channel filling frequency, and compare that to the avulsion frequency for the yellow, the Mississippi, and these other deltas, and see that it also follows this kind of scaling relationship. So we're starting to get out where and when avulsions take place. But it's kind of tricky when we think about the future, and that's because with accelerating sea level rise, a lot of these data are based on deltas that did not have accelerating sea level rise, which we know backwater effects are driven by, in part by sea level. So we basically need to understand the mechanics, the physics of this, and modeling is a great way to do that. We want to be able to predict these going forward. So we built this model for delta response to sea level rise that really resolves these backwater zone avulsion dynamics. Briefly, how it works is we imagine some starting point of a land and sea and a channel with known width and with a floodplain of known width. We solve for the backwater hydrodynamics along the long profile of that river, just using flow, mass, and momentum conservation under gradually varied conditions. We solve for the sediment transport in the river. This is just using England and Hansen 67 total bed material load. It just says the amount of sediments carried is going to scale with the Shields number. And then we also measure the deposition or quantify the deposition and erosion along the river using a Exner equation for sediment mass balance. And another two really important pieces of this are, oh, sorry, I should mention these three themselves form us what we call this morphodynamic cycle, where the flow drives sediment transport, which causes deposition and erosion, which changes the future flow, and so on and so forth. But we also had to add a few more pieces to this to tackle this problem. The first one being the delta front progradation. So we say at the front of the delta, basically the flow is no longer capable of transporting so much sediment, and it kind of dumps it out on this avalanche face. So it's using a shock condition to the Exner equation. And we also quantify the avulsions by basically breaking our delta down into discrete long profiles that represent different lobes. And what we do is we have one lobe active at a given time, and we keep track of how much that lobe has elevated itself relative to its neighboring lobes. So this is that same metric here. We're keeping track of how much the channel has it graded. And then when we say where and when the channel has it graded to some user input height relative to its neighboring lobe, so say half a channel depth higher, then an avulsion occurs at that place and time. So that's the start. And then we reroute the river downstream of that site to the lowest elevation abandoned lobe. So to give you a sense of what this looks like, here I'm going to play this video. This is an example simulation of the long profile for one avulsion cycle. So it's distance downstream, y is the elevation. The blue line is the water surface. You can see it's fluctuating. We basically need a variable flood discharge in order to maintain these backwater effects like in nature. And over time, the delta front you can see is prograding, and then the delta top is a grading as well. And then that happens up until this point where an avulsion is triggered here because we've basically built up sediment. We've elevated that lobe to 1/2 the channel depth relative to the other lobes. And at that point, it's going to reroute to a different channel, and then the cycle is going to repeat again. So we'll run this over dozens of avulsion cycles, and then and look at the results. So what I'm going to show you here in the next couple of slides are just is varying one model input, which is I call the dimensionless sea level rise rate. It's basically the sea level rise relative to the sediment supply. This is kind of ratio. And we're going to see what that does to the output avulsion length, just measured the sea to the avulsion site, as well as the output avulsion frequency, which is just we keep track of how often the avulsions occur in the model. So getting to these results, we see that at low rise rates, there's this progradation of the delta front, which drives the delta top deposition until an avulsion occurs. So this is an example with really, really, really slow sea level rise. So this is what sea level rise is 0.3% of the sediment supply. So it's basically negligible. And in this regime, the deposition on the delta is basically governed by how far it advances seaward. So it's called something that's called backfilling. And then here, an avulsion has occurred at this node, and then happens over and over and over again. And what we see is if we plot the avulsion frequency as a function of sea level rise rate, we can plot the average over many avulsions as a point here. And what I'm going to do now is going to vary sea level rise rate, and we're going to fill out this graph. So as we go to higher rise rates, we see avulsions occur more quickly because sea level rise is driving faster delta top deposition. So you can see our avulsion frequency is increasing with rise rate over here. And if we take this example on the bottom, this is a case where sea level rise was about 30% of the sediment supply, so it's significant. And you can see that this rise here has basically caused the delta to allocate some of its sediment resources to building up the delta rather than building out. So there's less progradation, and instead the channel's building up faster to keep up with sea level. And because it's building up faster, it's also avulsing more often. And this continues to occur as we increase rise rate further. So we increase the rise rate, delta fills up faster, less progradation, more aggradation, more avulsions. So we continue to increase the avulsion frequency, but things start to get weird when the sea level rise matches or surpasses the sediment supply. So here's a case with sigma star of 1. So now sea level rise is matching sediment supply. And what happens here, I'm going to show you this video, is we basically hit this new regime. So here you can see this mound forming. This is actually the mouth bars of the river. So the flow spreads here at sea level uh, at the river plume and deposits its sediment load there. And so what you're seeing is actually the river mouth retreating upstream on this lobe. And the river aggradation is shifting upstream over time up until an avulsion occurs here. So you can see the final shoreline and then the final avulsion node. This whole part of the active lobe was drowned here in this cycle. Um, and if we plot the avulsion frequency from this kind of simulation, we actually get the same value as the previous one. So we got a similar amount of aggradation, or sorry, we got a similar avulsion frequency, and that's because we basically hit this limit where all the river sediment loads going into the channel, and it doesn't really matter if you increase sea level rise more because it's already giving everything it's got. So together, this is painting this hypothesis, which is that there are these three regimes of delta response to sea level rise. This progradation dominated regime, the sea level rise in yellow, and then the supply limited regime in red, with the crucial thing being that in the yellow, increasing rise rate causes increasing avulsion frequency. Notably, if we look at all these regimes, the avulsion length is more or less the same. So the shoreline itself might move, but the distance between the shoreline and the avulsion node is going to stay relatively fixed. And you can see that from this graph here on the bottom. This is avulsion length versus rise rate. These simulations in white are roughly constant and scaling at about one half the backwater length here. And that's cool because if we actually assume that avulsions occur at this constant location and plug that back into our governing equations, there's actually an analytical solution that's a lot more easy to plug and chug at many different sort of conditions. But this is a bunch of modeling work, and it's really at some level just a test or sorry, it's just a hypothesis. So the next step is to how do we test this hypothesis? And one way to do this is to go to the lab. So we ran scaled experimental deltas, and these are really great for isolating variables like sea level rise and also looking at trends over many avulsion events. So here you can see this example. This is our flume that we used at Caltech River Ocean Facility. We feed water and sediment in at the upstream end, which flows through a 7-meter long by 14-centimeter wide river section and then debouches into a 6 by 3 meter basin, where over time it will naturally build a delta. We varied the flow discharges, durations in this experiment in order to maintain backwater hydrodynamics at the scale of a few meters. So basically fitting it in the tank. And we also had to scale the sediment supply in order to move sediment at basically such tranquil flows. And so for that, we used walnut shells, which are lower density than quartz sand. Over time, we quantified the avulsions on this delta as well as the shoreline. So here looking top down using from these overhead photos, you can see that over time, this delta has built out. Here's the land, the drowned area, and the sea, which has been dyed green for visibility. And we can map the avulsions by just keeping track of where the channels are and then noting when they change course, as shown by this yellow circle. We also keep track of the topography of the delta over time, both of the land and the water surface, using a laser altimeter and an ultrasound probe. And I just want to mention that this was a big effort, both in terms of the design and the construction of these experiments, as well as the implementation. So I want to give a shout out to my team members here, Jose and Sarah, who were really instrumental to getting these experiments done. In the next couple of slides, I'm going to show you some results from these experiments where we systematically varied the sea level rise rate over time, basically gradually ramping it up to target these different regimes that we think are important from the model. So looking first at a constant sea level case, I'm going to play this time-lapse movie here. Every second of this movie is about 2 hours of the experiment, so it's going to be super fast. Here's our initially empty basin. It's constant sea level. You can see the delta is starting to form and the channel it's channelized now. And it's migrating back and forth over time. And every once in a while, there's this jump in the river. That's the avulsion. And what we see here is that this is basically the progradational dominated regime here. So if we take the topographic data to compare to the pictures here on the bottom, this is our long profile of the delta over time from the channels themselves on it. And you can see over time the delta progrades, and that causes the delta to build up vertically. So it's that backfilling thing. Um, and over time, these avulsions occurred at these yellow dots, and I'm actually coloring them here from dark to light through time. So you can see that over time, the avulsions advanced seaward, sort of keeping up with the progradation of the shoreline on average. Um, and we can plot the avulsion frequency from this regime here on this gray square. And as we increased the rise rate, we saw that the delta transitioned to a rise-dominated regime with more frequent avulsions. So here's the same case with the sea level rise of 30% of the sediment supply. Saw a similar picture from the photos where the delta on average advanced seaward, the avulsions on average advanced seaward. But we see from the topography data on the bottom that here we're having less progradation, and instead the sea level is causing the delta to build up faster and so avulse more often. So the avulsion frequency increased too. We also saw that if we increase sea level rise further to exceed the sediment supply, we shifted into this sediment supply limited regime. And in this case, the avulsion frequency maxed out. So here's our avulsion frequency from that regime in gray. And we got to this point where basically sea level rises so fast that all the sediment gets allocated into the channel. And so it builds up as fast as it can. And the avulsions actually shift upstream as the shoreline retreats. So you can see that here. So all this to say that these experimental results are showing agreement with the model. So here's our avulsion frequency graph as well as the avulsion length graph again with the same x-axis of the rise rate. You can see that they're all showing consistency with these white model predictions. And it also shows consistency with the field data that we have for these kinds of rivers. So if we take the Mississippi, the yellow, and a handful of these other large lowland deltas where we have constraints on the avulsions, we can plot them as these yellow diamonds and seeing that we're seeing sort of this consistent picture for delta response of their avulsions to sea level rise. And if I was going to sum it up in one sentence, I would say that what we see is that deltas respond to sea level rise by avulsing more frequently and farther inland. And so this is important for thinking about the 21st century and how, as we have this accelerating sea level rise and land loss, there's this potential for not just the delta to retreat, but also the avulsion site to retreat. And this could potentially introduce new avulsion hazards to inland communities. So that wraps it up for this section. So briefly, we built this model and conducted these lab experiments to understand how deltas respond to sea level rise, accounting for the river avulsions and the backwater effects. They all are telling us that this basic picture that deltas respond to sea level rise by avulsing more frequently and further upstream. And that 21st century sea level rise is going to introduce more frequent avulsion hazards to inland communities potentially. So that's it for this section. I'm going to briefly shift gears and talk for just a couple minutes about some of my ongoing work, thinking about connections between rivers and the subsurface, specifically thinking about how we can defend floodplain and their soils against salinization hazards. And here we're going to be thinking about the effects of saltwater intrusion as well as sediment compaction. So starting with this example, I'd like to talk about how on May 26th of 2024, Cyclone Remal made landfall on the Ganges-Brahmaputra Delta. As a result, storm surges of up to 3 meters propagated inland and breached levees, causing widespread flooding and contamination of farmlands with saltwater. An example of this is here shown from Rampal in Bangladesh. So here's this example of a levee breach right here. And zooming out on the Ganges-Brahmaputra Delta as a whole, here's the location of Rampal and the track of this cyclone. As a result of this event, about 800,000 people were forced to temporarily evacuate their homes. About half of the standing crops were damaged, and more than 500 million in USD was lost in terms of assets and infrastructure, mostly in these affected areas here mapped by our colleagues at BRAC. And this leads to this question, which is how can we predict and defend against salinization hazards like Cyclone Remal in the future? Well, to first order, you can do what's called passive flood mapping or the bathtub approach. This is a simple way to basically estimate the potential depth of flood and salinization hazards, or alternatively, the levee height that's needed to defend against them. So what I mean by this is if we take an example profile from A to A prime across our landscape here, here's this profile and elevation. We can imagine having some surge of some known height, H surge, and then propagating that water surface inland to some point and saying, okay, what is the levee height needed here to defend against potential flooding? And we call this the levee defense height, or HDEF. It's just a simple subtraction. And if you plug in some values from the situation report of the cyclone, and we can actually make a map of where we think defense is needed for an event like this. And I'm going to update this thing on the left, and you can see that this defense height that's mapped from an equation like this actually does a decent job at overlaying what are the affected areas from the event. So the first order, at least, it does an okay job. But in the future, it's not clear if this is actually going to be the case because defending against flooding and salinization in the future is going to require us to potentially enhance levees or deposit sediment to keep up with these rising seas and subsiding land. So basically, our equation gets a little more complicated and our picture gets a little more complicated. So we're thinking about rising sea levels, subsidence of the land, and also potentially deposition of sediment on the land. And then so our defense is really the levee height and the sediment that we can potentially get. Um, and if we plug in some values for the next century, we can start to ask questions like, what is the defense map going to look like that we need for Cyclone Remol if it happened in 2100? And so I'll update it on the left to give you that image. And so basically what it's predicting is that the colors are warmer, so more defense is going to be needed. And also defense is going to be needed farther upstream. So you can see this or over in the northeast, there's this propagation of that signal. But I pulled a fast one on you here, which is when I plugged in the values for the subsidence. So here I just used the Holocene average subsidence rates, which we're understanding now that are not really suitable for making future predictions. So that's where we come in. So our team is measuring modern land surface dynamics in this joint campaign to disentangle the patterns of subsidence across the Ganges-Brahmaputra Delta, where a bunch of folks from universities in Bangladesh as well as the US and we're using a bunch of different techniques. So briefly, we're using GPS stations, both continuous and campaign, that have been mounted on these buildings and survey monuments for decades. These are shown in red on the map. We're also using rod surface elevation tables and marker horizons, which are really cool geophysical instruments that can help us distinguish between surface elevation change, shallow subsidence, and sedimentation at these sites. So these are shown in these yellow triangles. We're also using augering cores, boreholes, and strain meters to characterize the compaction of sediments and soils in the subsurface. Um, and also starting to look at using INSAR to potentially map surface elevation changes and higher resolution to really fill the gaps in between these field stations. And long story short, these results are showing that subsidence varies drastically across the landscape, which is posing a big challenge to predicting hazards. So here's a map of the measured subsidence rate from 0 to 25 plus millimeters per year. So you go in between different sites, which might be like 20 to 30 kilometers, and you can get anywhere from 0 to 25 plus millimeters per year, which is on anywhere from 0 to more than double the effective sea level rise here. So it's really big swings in subsidence. And this is in part because subsidence depends on things like the local deposition rate, the groundwater level, and the surface ecology, all of which is very naturally and due to anthropogenic land use changes. Um, and another important thing here is actually that subsidence varies with depth, which makes it really hard to compare the measurements from different methods. So we know that subsidence decays with depth just based on the mechanics of how subsidence and compaction works. But all of our different methods actually measure they basically measure subsidence over a different integrated depth interval. And so when we were trying to compare the RSET data to the strain meter data to the INSAR data to the GPS data, we come to this problem, which is we don't know how much of these patterns we see in the map are due to natural variations, are due to humans, or are due to just the different methods taking different pictures of this, different portions of this profile. So we want to disentangle its effect. And so for that, we built this predictive framework to really disentangle the subsidence observations. Briefly, how it works is we imagine some 1D sort of section of the Holocene compacting sediment deposits. So here's a borehole data for mud, and sand. We take nodes at the sedimentary horizons here, and we model how those nodes are going to subside over time using sediment mass conservation, taking into account the compaction of those layers due to a loss in porosity. We also use constitutive relations to keep track of the porosity as a function of the effective stress. And the effective stress is basically how much overburden weight we have on a given layer. And then you also account for the resistance to that overburden due to the pore water pressure that can build up in between the grains. And to get at that pore water pressure, we have to model the groundwater flow, thinking about momentum conservation and these basically Darcy's law. Um, and to apply it to a place like Bangladesh, these densely populated deltaic regions, we have to account for the water table fluctuations. So thinking about how the monsoon and how groundwater irrigation and drinking water can affect the pore pressure state. And also the effect of the surface ecology. So the tree roots and the burrows in these, especially in these forested areas, can take up a large portion of the shallow subsurface, which is basically porosity. So it's places that the sediment is not occupying because of the biology. And you need to consider this to get the mass balance right. And the output of the model like this is basically a profile of the predicted subsidence rate as a function of depth. And this is cool because we can basically integrate it across an arbitrary depth interval and compare it to our methods. So just getting right to the chase. So our results are showing agreement with about 2 decades of our field observations. So if we look at our field network on the left here, I'm going to plot, especially near Rampal, we're just going to focus for now for these data. We're going to plot the observed rates versus the predicted rates from the model. First for the RSET data shown in yellow, and then for the strain meter data in blue, for the INSAR data in gray, and for the GPS data in red. And so at least for this site, we're seeing this agreement between the predicted and the observed rates, um, which is pretty interesting and cool. And one of the things we can do with this is actually start thinking bigger picture and taking an analytical solution to this model now that we have some faith in it. Um, and basically, this is the analytical solution to the model. And if we plug this in to our initial levee and defense height problem from earlier, we can start to inform where and when we might need to build levees higher or divert more sediment in order to defend these coastal lowlands in the future. So what I mean by this is we can take this analytical solution, plug it in for the subsidence, and then rearrange to isolate the variables. You get this equation at the bottom, and we can update our map using that equation. So here's our map from earlier for Cyclone Remo in 2100 without compaction, and here's when we add this compaction model. So you can see here the colors got warmer, so it's telling us that basically by 2100, defending against a cyclone like Remo might require 3 to 5 meters of height gained by sediment and or levees. But importantly, there's some new hotspots too. So there's these red zones here and here. And these are actually situated above buried paleo valleys. So if we lay the Holocene isopachs here, and also I'll just draw for you the basically the minimum here, which are telling us the ancient paths of the Ganges and the Brahmaputra paleo valleys that were carved during the last glacial maximum. These are overlaying the hotspots of the defense. So basically, there's this legacy of the ancient climate change that's affecting the modern day hazards. I just want to mention that this ongoing work is supporting these climate change adaptation plans to secure freshwater livelihoods and flood shelters around lowland Bangladesh. So we're a team, we call ourselves GeoCruiseNet. We're a consortium of universities in Bangladesh and the US, as well as large NGO BRAC with 90,000 employees and we're working with our climate change adaptation division to basically take our impact assessments from these data analysis and turning that into evidence and fuel for their proposals, clinics, and decision-making processes to eventually get us to these sustainable community solutions there. And yeah, that wraps it up for my talk. So we talked a little bit about these linking rivers and the subsurface, as well as river mobility and river deltas on these 3 questions. But I'm interested in a lot of other questions on these topics related to river systems, humans, climate change, and such. And I just started at the Columbia Climate School, this new lab, the Roar Lab, and I'm looking to hire a postdoc this year. So if you're interested, please reach out to me. Thanks.
Wonderful. Thank you, Austin. It was great to review this again. Um, all right, so it seems like we already have a question in the chat. So I'll just read it here. Related to the third topic, have you applied similar modeling to the Wax Lake Delta?
Oh, for the subsidence and like defense height modeling? No, I have not done that. That would be very interesting to do. I think one of the things that's been interesting applying it here in this place is thinking about what's similar and what's different from other deltas. And I think that for coastal Bangladesh, the Ganges Brahmaputra is really sandy. So Holocene sands don't compact too much compared to Holocene mud. So going somewhere like the Wax Lake might be really different because I think there's a lot more mud. So the sort of response time and the magnitude of the subsidence could be really different.
Fantastic. Thank you, Austin. Christian, do you have, or Laurent, do you have any questions while people um, are putting their stuff on the chat?
Yes. There is one question which I can maybe read out. So also thanks for your great talk. In your model, you do account for variable compaction related to subsurface organic matter, or is
Mhm.
it accounted for in the mud?
Say again? How is it accounted
In
for?
your model, do you account for the variable compaction? So I think it's linking to the
Mm.
subsurface part three.
Yeah, that's a really good
Um,
question. Yeah.
and so what about the organic matter? Is that part of the subsurface, or do you put it part in the mud?
That's a really good question. So that I think that is so it's an ongoing work. And the way that we're going through it right now, the approach that we're taking, which I think is right, but definitely we're building on it and working with soil scientists on this, which is including the organic matter content as part of these biogenic effects. So this is basically not plastic sediment, and it's sort of being treated as its own material, and we say this is how much space it takes up as a function of depth. And this is really a good estimation in this delta, at least, because there's very little organic matter beneath the soil column. And so we can basically break it down into muds, sands, and then shallow subsurface where there is organic matter. But some deltas, you have a lot of organic matter that gets preserved, and for that case, you might need to take a little bit of a different approach and maybe assign it its own lithology like peat and stuff. Yeah.
I maybe also have a quick question, if you don't mind, for your first topic, this river mobility, which I think
Hmm.
is really inspiring, where you show that some maintain their cross-sectional width and some are actually widening.
Hmm.
What would you call, or what would you identify as a process for that? Like previously, the bank stability was linked to vegetation and deposits of fine sediments. Is that something you would also support, or what's your turn on
Yeah,
that?
I mean, I think it makes sense. I mean, the vegetation can help stabilize the banks and slow down the erosion. I think it's consistent with this picture that we see where the more basically it's single thread if the erosion is slow and at pace with the deposition. I think that at the end of the day, this approach that we took here with the remote sensing is actually not the approach that's best suited to tackle that problem because you can't really see what's going on at the bank from satellite. So I think really what I'm excited about is thinking about how we can take this further doing field work and modeling and experiments to really understand how these in, runaway widening and with equilibrium are modulated in part by plants and potentially other stuff. Yeah.
Thank you.
Laurent, do you want to take that one?
Sure, yeah. New question from Andrew Wilcox. Great talk. Are you planning to use NISAR to measure subsidence?
Yeah, I would love to. I'm working with some folks at Lamont Doherty Earth Observatory, including Lin Shen, who's a postdoc there now, who's an expert in those kinds of satellite data and techniques. So I'm not a whiz with NISAR and these radar stuff, but I'm working with people who are, and I'm very excited to dig in to see what we can learn from it. I think that one of the things that's been really I'm excited about is thinking about the spatial scales of variability in the subsidence rate because I think that no matter how much field data we have, it seems like it's not quite at this, we're not quite getting resolving all the variability. So I think this kind of data is going to be great for that. Thinking about when you pull up the groundwater here, is that how does that cut? Is like the cone of depression of the groundwater the same as the scale of the variability of subsidence, or is there some other stuff going on? Yeah.
Great. We have another question here from Hongbo Ma. Hi, Austin. Great talk about the first topic. How could we know which one drives another between belt widening and in-channel bar formation? So which
Yeah,
one, what drives
that's a
what?
good that's a good question. I think that sort of similar to what from the previous question, I think the understanding the cause and effect of the bank erosion and the bar uh, development is remote sensing might not be the best approach for that. But I think that it's really important. So I think you're getting at this problem, which is that we don't really know what's going on underwater from these kinds of analysis. So that's excess eroded sediment from the banks. It's got to go somewhere, probably going onto the bed, building up these bars. Those bars might help facilitate more erosion. Um, So maybe the bar itself is helping get you this instability, but I think there's definitely feedbacks there because we know that the bars are more likely to form when the channel gets wider. So maybe there's some interesting positive feedbacks there. Yeah, good question.
Wonderful.
I actually
Uh,
have one question. In the diagram you had at the very beginning, showing sort of the different areas of the rivers you look at, you had a dam way upstream, and I'm kind of wondering with the sediment compaction for your defense height,
Hmm.
uh, is like subsidence or compaction, is that sort of also uh, taking into account the effective changes in sediment supply to the delta from, like, for
Hmm.
example, dams upstream or
Mm.
levees?
Yeah, that's a good question. So I think one of the things I'm excited about with taking this approach for the defense height is it actually doesn't have the sediment in it at all. It's actually kind of the thing that you're solving for. So we took the sort of relative sea level rise equation with the rise and the subsidence and the sediment, and we just rearrange it so that the things we don't know, namely the subsidence and or sorry, namely we don't know how much sediment's going to get deposited and we don't know how we're going to build a levee, but we solve for basically the height of the sediment and the levee that's needed to counteract subsidence and sea level rise and floods. So what I would think about it is like in those maps we're showing, that's telling you how much sediment we need to get deposited in a given pixel. And changing this, building a dam upstream means there's going to be less sediment available. So maybe we're not going to meet that defense height. And so I think the way to think about it is like sort of the defense height's telling you how much sediment you need, not how much you have. Yeah.
that's great. All right. So, is unless anybody else has any burning questions, Christian or Laurent or anybody in the chat, um, speak now or you'll lose your chance. I'm sure you can get in touch with Austin.
Right.
Um, and big shout out there for looking for postdocs. So let's whoever is looking for one of those opportunities, Austin is waiting for you. Uh, okay, so I think that wraps it up. We're at the top of the hour almost, and so let's thank Austin once again. And thank you all for coming. We'll see you next or in a couple of weeks. We're going to send out an announcement about next week's talk soon, which unfortunately we're going to have to cancel. But yes, wait to hear from us. Thank you again, Austin.
Thanks again. Thanks everyone. Thanks to the organizers.
Yep.
Thanks.